Okay, hello everyone. My name is Amy Dunn, and I'm going to be talking about automating contour generation with a model builder workflow using high resolution elevation data in a mosaic data set. So I work for the New Mexico Bureau of Geology and Mineral Resources, which is a research and service division of New Mexico Tech. We function as the state's geologic survey, and we have a lot of different programs at the Bureau, but in my completely unbiased opinion, the GIS services program is the best one. So we are responsible for publishing our geologic maps and the associated GIS data. We adhere to the USGS GEMS data standard, which stands for Geologic Mapping Schema, and the Federal Geographic Data Committee's cartographic standards for geologic maps. We perform QA/QC on the geologic maps all the way from the creation of a map kit through data validation and the final cartographic layout you can see on your screen. The Bureau has generated its own contours for our maps since around 2012 because our geologists did not like the level of smoothing the contours had. The USGS uses 1/3 arcsecond DEMs, which is about 10-meter resolution. And generating our own vector contours gives us control over the level of smoothing, the symbology, and the labeling. So I have two USGS topos displayed here, and you can see how smooth the 2010 version is compared to the most recent 2023 version. The 2023 version also has a whole bunch of labels on it. And these are available in PDF form. So once we get these, we can't really edit them. So that's why we like the vector data. So I'm going to use Model Builder in ArcGIS Pro to automate our current multi-step contour process. For some background, our current workflow involves semi-manually selecting the elevation rasters that we need for our map areas. We do use the Select by Location tool to select the raster footprints, but then you have to go into the attribute table and write down the row and column number of the raster you need and add it to your project. Most maps you only need one raster for, but sometimes they fall on the boundary, so you need to mosaic multiple rasters together. New Mexico is mostly in NAD 83 UTM zone 13, but we do have a strip on the west side in zone 12, and some of our legacy maps are still in NAD 27. So sometimes you need to project the raster data. But after that, you clip the raster to your map boundary, you build the contours. We also have developed a process for simplifying the contours, which improves performance in ArcPro and when we export to Adobe Illustrator for cartographic work. But then you append your contours into a GEMS compliant feature class and calculate the attributes. I'm going to recreate this process except for the simplified contours portion because that was just a lot more complicated and beyond the scope of this project. So the first thing I needed to do was get some input data for the model. I set up a map kit, which is shown in the left-hand column. This is our folder structure for a map kit. And I have the ARC folder expanded, which contains all of our GIS data. On the right-hand side here, I have a GEMS compliant geodatabase. And the feature classes we're going to be concerned with for this project are the map extent poly, which is going to be buffered by 1,000 meters, and then the contour lines XX feet feature class. So I chose 2 study areas in southern New Mexico to test the model. I got the map boundaries from the USGS 7.5-minute quadrangle index, which you can download from the national map. The first one I chose is Sierra Blanca Peak. I picked this one because I think this is one of the steepest areas in New Mexico, and I didn't want to do a contour project in a flat area. It is in the same projection as the elevation data that we have. So I figured if I could get that process to work, we could deal with projections later. It's at the intersection of 2 of the elevation rasters shown in the lime green, and I used that to test the mosaic process. I also chose Grouse Mountain over here on the west side of the state because this one is in UTM zone 12 and was useful for testing if the projection worked. And it's also at the intersection of 4 elevation rasters. If I zoom in here to the northwest corner, I ended up building 4 map kits, which I did the current methodology for each one and built rasters and contours in both NAD83 and NAD27, so I could use these to test against the model results and make sure they were consistent. So the second piece of input data I needed is elevation data. The Bureau has acquired theirs from the U.S. Army Corps of Engineers. We refer to it as the SPATM data, which I discovered what that stood for during this project. So this image here is the South Pacific region that the U.S. Army Corps of Engineers manages, and our data covers the Albuquerque district in red. So it's South Pacific Albuquerque Digital Terrain Model. Our data is at 4.5 meter resolution, which is about twice as good as what the USGS uses. It comes in 152 image tiles and is, again, in NAD83 UTM Zone 13. So the first thing I did was create a mosaic data set for all 152 of those images. This tool here on the left is what creates that, and you can set your coordinate system. It doesn't have to be the same as your original data. So I originally made 4 data sets in each of the coordinate systems. Then there's a whole bunch of mosaic data set properties you can set, but these 4 I have listed here on the side are what were most important for our data. After that, I use this center tool to add the rasters to the mosaic data set. This checkbox here at the bottom that says estimate mosaic dataset statistics never really worked. Whether I checked it or unchecked it, it never produced the correct results. So I also had to calculate statistics after the mosaic was built. After I got the mosaic built, I wanted to know if it was producing the same consistent results as the original method. So I used the raster compare tool, which outputs a text file with a bunch of raster properties and basically says whether they match or not. The NAD83 Zone 13 one that matched the elevation data did match. The other 3 did not. So then I wanted to know where they weren't matching. So I used the equal to tool, and that produced the raster you can see on your screen, which is mostly gray, which indicates no change. But there are some red pixels where the pixel value or the elevation changed. If I zoom in, you can start to see these little specks of red throughout the entire raster. This shows that it's not just the mosaic data set that's producing a different result, because they're not just in this overlapping area between the green lines, they're throughout. I also wanted to know how different they were. So like if it was just 0.00001 meters off, that might not have been significant. But I ran the raster calculator tool to calculate the difference between the original rasters and the mosaic data set. And some of them were only a couple meters off, but when you get into NAD27 Zone 12, they were almost 50 meters off, which I thought was pretty significant. So I decided to only do 1 mosaic data set in the original coordinate system, and we'll project the contours later. Once the contours are built, I wanted to compare them again to the original, and I used the feature compare tool to do that, which puts out a text file and basically says whether they're the same or different. I also wanted to make sure the projection was working, and that is going to be handled by the append tool in the model. So this is my model. I'm going to expand this really quick so you can kind of get an overall view of it. The model does produce contours in feet or in meters. And the only reason I have the Starship Enterprise in the background here is I thought the different branches looked like the nacelles of the spaceship. Going back to this view, I'm just going to go through this kind of briefly and point out some issues I had. The first tool that runs is to clip the mosaic data set or your input raster down to your map area using the output extent with that buffered map extent poly. You can choose which folder to store the raster data in, and this map name parameter is used as an inline variable throughout the models to name different outputs. It's also important that you set your environments for this model, because it also uses the current workspace and the Scratch workspace as inline variables. This use input features for clipping geometry parameter I did not want to set as a user-defined parameter, but I had to because this tool won't let you check it by default until you have an output extent set. The next thing the model asks is whether you want to convert meters to feet. And then it separates into these two branches. They're nearly identical. The feet branch starts out with a raster calculator that converts the meters raster into feet. Then they both generate the contours using the contour tool, and the contour interval is a user-defined parameter that people can set. This calculate value tool and the output it has is only so I could make a shorter variable name. Because down here in the center, I need to rename this contour lines XX feet feature class to something like contour lines 40 feet. And the alter field tool to alter one of the field names inside it as well did not work with the longer variable name. After that is complete, the contours are appended into this contour lines feature class. And this append tool also handles a couple of the attributes with the field map. The rest of the model just calculates attribute values. This next parameter here is an SQL expression you can write to select your index contours and then calculate the index symbol. The selection is switched so you can calculate the intermediate contour symbol. And then the selection is cleared so you can calculate your data source ID. This is a GEMS prescribed field, and all the GIS team members and the geologists have a data source ID code, and it basically says who created that feature. The last field it calculates is a underscore ID field, which is also a GEMS field that we have a code block running in the background, and it calculates a unique value for each feature. Back on the meter side, there's one more calculate field that runs. The value confidence field shows the vertical accuracy of the elevation data, and the database is set up to do 3 feet by default, but when you want contours in meters, we need to recalculate that to 1 meter so that it matches the units of the contours. For my results, this is the final mosaic data set I ended up making. It eliminated using the mosaic to new raster tool and the project raster tools for the model, so it simplified that a lot. We do have an image that's already been mosaicked of this entire data set, but this is like a quarter of the size of that image. And I think this will be useful even outside of this contour making process, and it is currently available on the Bureau's network for anybody to use. I wanted the model to run as a geoprocessing tool, and it's fully documented. There's tooltips that come up that tell you how to fill out each field. I created these feet and meters categories, so you only need to expand the one you need. But I did have to put in some like default values, which are shown here on the right, because the tool would not run if the other branch was blank. I tried to copy this tool over to our network at the Bureau, and it does not work. It completely broke. I could not get it to work. I couldn't get the model to work. And I went back to my personal computer, and it still doesn't work, even though I did get it to work at one point, but the model still runs. So I was able to produce contours. This is 80 feet contours for Sierra Blanca Peak. And if I zoom in, I've got the model contours in blue and the original contours in tan. And you can see that they line up very well, and the feature compare tool confirmed that they were the same. When I zoom in over here to Grouse Mountain, I have the model contours in NAD 83 in blue and in NAD 27 in pink. And you can tell on the interior here they line up, which is expected. And this offset you can see on the left is because of that difference between NAD 27 and NAD 83 in the map boundary. So in conclusion, Model Builder does have some limitations. There was oftentimes I couldn't find tool documentation. It's not as flexible as Python would be, and I think I'm going to end up having to export this to Python to get it to work on our network, and to get it to either run as a model or as the geoprocessing tool. And I would like to incorporate the simplification process. Currently, we simplify the line work, but I read about a lot of ways to simplify the raster before you generate the contours. And I think that might be easier to incorporate into an automated model like this. But overall, the model advances the GIS Services Program's goals of producing scientifically accurate and high quality cartographic geologic maps. And I would like to thank you all for coming.